My daughter's getting married on spring break, and so Daddy had a little fun. So yeah. So she she doesn't know what I did. She doesn't know what's going on. She says, "Yeah, I know Dad's going to do something, and I'm going to hate it." No, you're not going to hate it. She's just worried. I just hope he doesn't do it during the wedding. She thinks I'm going to ruin her wedding or something. I don't know, but yes, Dad's going to have some fun and do something cool. So, all right, let's look at our lesson this week for everyone that's here. Uh, and yes, you may notice my shirt I'm wearing today. It's like, what in the world, Mr. Brock? 4E 65 72 60. This is hexadecimal. This is hexadecimal, so we can look at what I have written on my shirt in hexadecimal as we get into this lesson here. So let's take a look at the lesson. Then before we leave, I'll decipher this for you. All right, so pulling up on our screen, our Foundations of Programming class. There it is. Go to our grade screen as usual. All right, you should have, see, Module 4 project. That's what was due last night. Should have everything turned in from Module 4. We're completely done with that. We've done all the assignments, all the programs. You should be ready for Module 5, number systems, hence the shirt, hexadecimal. Number systems. So we have 4 lessons here we're going to look at in codes and objects, starting with 5.01. So let's go check that out now. I'm going to close Module 4 since we're through with that. Open up Module 5. And let's look at our number systems lesson. All right, types of numbers. How many teaspoons are in a mile? Anyone know that one? Anyone know? Anyone? No. How many teaspoons? How about your height in gallons? How many gallons tall are you? This isn't typically how you would measure distance or height. You'd probably figure out a way to convert the numbers if you had to do that. So in programming, there's a few different types of numbers. Some are used to represent symbols. Others are used in calculations. Some are used for colors. Computers use hexadecimal actually for colors and for memory locations. So we're going to learn how to describe how different number systems are used to represent data today. So looking at page 2, our world runs on 2 things, language and math. Probably math more than language most of the time. We use language to communicate, and we use math to do pretty much everything else. I mean, think about it. If you're an architect, you need words to describe what you're doing, but you need numbers to make it work. Architects, a lot of numbers. If you're a musician, words come in handy for lyrics, but numbers arrange the music and set the tempo. In programming, the type of number used depends on the type of data that you're using there. Each number system has a different base, which is the number of digits it uses. Like we commonly use the decimal number system. It's base 10, right? That's what our world operates on around us. Base 10. So it uses 0 through 9 as the 10 digits. It has 10 digits. It's base 10, 0 through 9. So let's check out some of the different number systems. Decimal system, base 10. It's the most familiar. 0 to 9. Money uses decimal systems, as all amounts use numbers based on the 10-digit system. $1.50, 1.50. Binary is a computer language, base 2. It only uses zeros and ones, 2 digits, zeros and ones. Binary numbers are what the computer languages are made of. It's the most basic language. They are based on the 2 digits, 0 and 1. The combination of zeros and ones can be converted into other types of numbers or even words. You can write words in binary. Like you can use the binary system to write other types of numbers or words. So 0011 0001 0011 0010 0011 0011. That is 123 in decimal. If we convert it to decimal, it's 120. Now you see why we use decimal and don't use binary, right? Woo, man. So yeah, that's how you write 123 in binary right there. Hexadecimal is actually a base 16. Imagine if our life ran on base 16. You'd have to do a lot of things. I guess if we were used to it, it might be fine. Hexadecimal numbers are common in the computer world. Computers use a lot of hexadecimal, mainly with colors and memory locations. They are based on 16 digits. It goes 0 through 9 and then A through F. So if you're counting in hexadecimal, You'll go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. That's the 16 digits hexadecimal uses. Like if you ever looked at the HTML code and stuff for colors on a website, this is like a color right here. It'll have hashtag FFD700. That's hexadecimal, and that is the hexadecimal code for the color gold. So something gold on the screen, the computer would say, okay, that color is FFD70000. So it uses the hashtag with 6 digits after it. That is the hexadecimal, how computers store color. So computers use hexadecimal all the time. And everything's converted to binary for a computer to understand it. I love this. I should get one of these shirts. I see these. There are 1-0 types of people in the world. 0-1, those who understand binary. 1-0, and those who don't. See, that's a binary 2 right there. 1-0 is 2 in binary. So it's saying there's 2 types of people in the world. 1, those who understand binary. 2, those who don't. So it's just written in binary. Love it. Look, things aren't always hashtag 00000 and hashtag FFFFF. The great thing about the different number systems, you can convert one from another. If you have one type in decimal form, but you need to use a system that only reads binary, like a computer, you can do that. In the decimal number system, each place value is the power of 10, right? We have our 1s, our 10s, our 100s, our 1000s. So the column 10 is the power of 1, all of that good stuff. The same is true for binary. One easy way to convert is to use an online calculator, but you can find lots of calculators to convert from decimal to binary, decimal to hexadecimal, binary to hexadecimal, all kinds of stuff. There's also a nifty way to do conversions on your own without the computer. So it says, all right, get a marker, you're going to draw on your fingers. Okay, you don't have to draw on your fingers, but here's a little fun way to do this. All right, so hold up your non-writing hand. If you're right-handed, you hold up the other hand. And starting at the leftmost finger, which if you're right-handed, that'd be your thumb, I guess. That'd be the leftmost. If I'm left-handed, it'd be my pinky. Write the decimal numbers 16, 8, 4, 2, and 1. One number per finger. So the number on the right would be 1. The number on the far left would be 16. These are all powers of 2 because we're converting to binary. This is the 1's place, then the 2's place, the 4's place, the 8 place, the 16 place. Because it's not based on 10s, it's based on the powers of 2. So when a finger is raised, it represents a 1. Right, just the far right there. When it's down, it represents a 0. So if you close your fist, you're showing 0 fingers, and we call that 0, 0, 0, 0. If you lift all your fingers, that's a 1, 1, 1, 1 in binary. So you'd add all those numbers. So you have a 1's number, a 2's number, a 4's number, an 8's number, and a 16 number, and you add all up, and you get 31. So on one hand, you can count from 0 to 31 on one hand. Just depends on which fingers you have up. So select the images below to see more examples how you can convert binary numbers. So if you have all of them up right there, that's binary for 31 because every one of those is added in there. If you close this one down, now we just have the 16, the 8, the 9, the 4, and the 2. So that's 30. You just subtracted 1 from it, right? Binary number for 30. Here, you just have the peace symbol up with the way they have it written in that direction. You got a 2 and a 4. So that's the binary number for 6. Here's the binary number for 3. You just have the 1 and the 2 up. And then finally, if you just want to say 1, how many you want? 1. Just the decimal number 1 showing. So you can do all of these. And there it shows the binary equivalent underneath. 1, 1, 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1. That's how you would write it in binary. But that's the numbers that it's equivalent of in decimal. So can you come up with the binary number for 12? Well, let's see, 12. We need an 8 and a 4, right? So you just hold those 2 fingers up. So it'd be 0, 1, 1, 0, 0. 8 plus 4 equals 12. 0, 1, 1, 0, 0. So that's kind of how binary works. It's all powers of 2. Decimal is powers of 10. So hexadecimals, yes, is powers of 16. Crazy stuff. Binary to hexadecimal. So 16 symbols, 0 through 9 and A through F. The number system is a base of 16, which makes an ideal way to represent a binary number, but with fewer digits, because 16 is a power of 2, and since binary is based on powers of 2, hexadecimal is a shorter way to write that. So let's see. If we have 11000111, so over here, 0111 is binary for 7 in decimal, which is 7 in hexadecimal. In hexadecimal, you just call it a 7. So this number is binary right here. 1100, that's 12 in decimal, which is C in hexadecimal, right? Because you got 9, A, B, C. A is 10, B is 11, 12 is C. So C7 is all you need to write this long binary number. C7. So for every 4 binary digits, that's 2 to the 4th power is 16th. So you can take every 4 digits and convert it to a hexadecimal number. So 1100 converts to C, 0111 converts to 7. C7 is the hexadecimal equivalent. So the good news is the hexadecimal numbers are much shorter to write than binary numbers, which is a huge time saver. Let's take a look at the binary and hexadecimal numbers for 15. Which would you rather type out? If you're writing in binary, it's 1111. In hexadecimal, it's F, because that's the biggest number in hexadecimal. That would be 0 to 15 is the span. Just like in decimal, when you get base 10, it's 0 to 9. 10 is actually the next level. All right, comparing. Here's a nice way to compare the first 15 numbers. So in 0, it's pretty much the same all across. 0, 0, 0, 0, 0, 0. 1 is 0, 0, 0, 1, or just 1 in hexadecimal. So look, the first 9 decimal and hexadecimal are exactly the same. Binary, you got to start filling in the other zeros with 1s. So 9 is 1001. Then we get to 10. That's when hexadecimal switches to A, B, C, D, E, F. But that's just 10 through 15. Where binary starts getting more, the bigger numbers on the left start getting to be 1s, till finally you have 1111 for 15 there. So let's play with that in programming. So converting in Python. So now you understand the different number systems, or at least you've been exposed to them a little bit. You can probably tell that they would take a while to figure out in your head. If I say, okay, what's 88 in binary? What's 88 in hexadecimal? Okay, you're going to have to get a pencil and paper and do a little work. But that's another area where Python can save the day. So it has these 2 commands, bin with parentheses or hex with parentheses. So let's look at this simple code right here. Age equals 17, right? That's just, we're assigning a value to the variable that we called age. Age equals 17. Now we're creating another variable and we're calling it binary age. That's just a name we made up for the variable. And we're setting it equal to the binary equivalent of whatever age equals, which in this case is 17. So that'll tell us what the binary of 17 is. And then when we print it, it'll print it out in binary. So let's try converting different number systems. Looking at their sample programs right here. All right. Hashtag number systems. Let's read this over and see if we can predict what it's going to put out. Define main. So start our program. Our main function is defined. Now note, this is a hashtag. So these are just comments added into the program to help people read the program. So it says this code right here assigns a decimal number to D. So D is our variable. So it's assigning the number 7. And then we're printing that. The decimal value is, and print whatever D is. Now remember, we have to use that string in front of str because we're combining it with letters. So we got to tell it, treat that number just like it's a letter and print it. So we print the decimal value of this number. Now, hashtag comment, convert D to a binary number. So B is going to be a variable, and it's going to be equal to the binary equivalent of whatever D was, which in this case is 7. Then we're going to print the binary value, and we're going to print B because it's stored as a binary number. And that's the end of the program. So let's run the program, see what it looks like. The decimal value is 7. The binary value, now notice there's a 0B first. Like, wait a minute, there's no B's in binary. This is how Python says, by the way, the number I'm about to show you is a binary number. It's not decimal. If it just printed 111, and we just had something where it just printed out 1, it's like, oh, that's 111, right? Python is saying this is not 111. This is a binary number 111. So that's how it denotes the following number is binary. It puts a 0B right in front of it. So anytime you see that 0B, you know, okay, what follows that is binary. All right, it says change the value of D to any integer and see the result. All right, let's say it's going to be 60. Let's run the program. If it's 60, it's the binary number, 0B, 111100. That's 60. How about just the number 2? 10. How about something fun like 2,159,620? Can we print that in binary? Oh, yeah. 1000011110100000000000000. So that's 2,159,620 in binary. Starts to be some real calculations. We're not used to thinking in binary, but this is the way the computer calculated it before it printed it in decimal, because computers do everything in binary. All right, let's look at the next sample program here. Let's read over this code. Define main, assign a decimal number. So we're back to assigning our 7. We're going to convert it to a binary number, just like we did before. B equals the binary equivalent of D. And we're going to print that out. So nothing's different so far, other than we didn't print the decimal. We took that out. Now we're going to convert the binary number to a decimal. So it's saying hashtag. We're going to have, it works as integer, whatever the number is, and then what base we want to use. So we're saying the integer is B, which is a variable, right? That is the binary number that we stored in B. So it's saying this binary number in base 2, which is binary. And it says print the decimal value is string D. So this is converts it to a decimal. This command right here, convert it to an integer, convert it to a number that I recognize. So take this binary number that's in base 2 and make it something I can understand. Oh, sorry. Make it something I can understand. Run program. Binary is 111. The decimal is 7. Nice. So let's say, what if we just change that to a 88? That's 1011000, but that's an 88. By using the integer command, take the binary number, and we could just put the binary number right here, 01100. How about that? What is that? Isn't it? We can just say whatever this binary number is, and it's binary. We're telling you it's base 2. Print that as an integer, so I know what it is. Oh, non-string. I did something it didn't like. Split space on line 14. Okay, I guess I have to leave it as the variable for now. Oh. So that's why I did it that way. Okay, so make it a variable. It'll take the number, base 2. Didn't like how I did it. All right, let's look at the next one. Again, we're going to assign a decimal number. This time we're assigning the number 156, and we're printing that out. All right. Now we're going to convert it to a hexadecimal number. What is the hexadecimal equivalent? The hexadecimal equivalent is whatever, H. Now, interesting. Notice we didn't have to put string in front of it. Also, there's going to be an error, one or the other, because we didn't put an str in front of this. But we had to use str down here when we convert it back to a decimal. Take whatever the number is in the base, so whatever H is in base 16, and make it a decimal again. So 156. Now notice for hex, it puts 0x. We had 0b before binary numbers. 0x precede hexadecimal numbers. So the number 9c is equivalent to what decimal? 9c is equivalent to 156. So we can use letters as numbers. And notice it has no problem printing that out without the STR. We don't have to do the STR when printing a hexadecimal number. In fact, let's see if that causes an error. I haven't tried that. If I tell it to print it as a string, it has no problem. You just don't have to. It still runs. There's no error there. But apparently it's not needed with hexadecimal, because that's a language that the computer already speaks. All right, next slide. User input now. B equals 0b, because that's how it recognizes that's a binary. And we're going to enter a binary number. Oh, that's why I had an error on that last one. I didn't tell it 0b in front of it. If I'd have put 0b in front of it, it wouldn't give me the error. I didn't do that. So print your binary number is. So it's going to add that in front of it. Then it's going to convert it to a decimal using the number and the base. Print the decimal equivalent is. So let's run this. Enter a binary number. 101101. Okay. So it's 0b 101101, which is 45. So a nice way to figure out what in the world is this as a decimal number. It's 45. Want the computer to help you convert a binary to decimal? Making the program interactive is a great way to do this. So we just added the input statement. Instead of assigning a value, we added the input. So we could put whatever number we want to do. 111111110. Okay, that's 510. So a nice little program to help you convert. Let's look at the last example. Okay, print table heading. So it's going to print number systems chart. It's going to print decimal, binary, hexadecimal. And this is going to print the body of the table. So for D in range. So we've created a loop that runs 16 times. Right? It runs from 0 to 15 and it stops when it gets to the 16. So we've got a loop. So B is going to be the binary equivalent of D. H is going to be the hexadecimal equivalent of D. And D is the loop number we are on. So D is going to start with 0. Then it's going to be 1 and 2 and 3 as we go through the loop. And this is going to calculate the binary and hexadecimal equivalent and print them. Print, and they're spacing it over, trying to line it up underneath these headings that they printed. So they put spaces between them. But print the decimal number, then the binary number, and then the hexadecimal number. Notice we don't have to have the string on the binary or hexadecimal, only on the decimal number. Let's run this. Oh, there we go. Number systems chart, decimal, binary, hexadecimal. 0 is just the binary number 0 and the hexadecimal number 0. But as it goes down, notice the binary number starts getting wider and wider, so it pushes our hexadecimal away. But the last one is 15, which is the binary equivalent of 1111 and the hexadecimal equivalent of F. So there's a nice little program that'll give you the first 16. Let's change the loop and make it bigger and see what it looks like if we went to 100. Let's print the first 100. Now when we run it, okay, let's go down like 77. 77. 77 as binary is 1001101. In hexadecimal, it's just 4D. 4D is 77. So 100, it goes to 99 because my loop stops when it gets to 100. So 99 is 11000011, or it's 63 in hexadecimal. All very different. All very different. All right. Let's look at the assignment because that's the end of the lesson. Page 6 just says read the lesson. Practice on that page we just left. You can practice and then do the quiz. So we go to the next item. 1, 2, 3, 4, 5 questions. 5 questions about what we just read. Right? Binary, which systems represents 15 as a decimal? Which of the following represents the numeric value 15 as a decimal? Please don't miss that. How do you write 15 as a decimal? Not as a binary, not as a hexadecimal, as a decimal. Please don't miss that. What's the purpose of hex functions? Read this code. What will it output? Read this code. What will it output? All right. So I told you, I said, all right. So I'm wearing hexadecimal 4E 65 72 64. There is a alphabet equivalent. And I found a table online to show you this. Let me show you this table. Oh, my daughter gave me the shirt for Christmas. Okay, it looks a little weird, but on the left side of the column, over here in the far, far left, this is the first digit of your hexadecimal. It's either 0, 1, 2, 3, 4, 5, 6, 7. Then on the right side is the 0 through F. So the first thing on my shirt is 4E. So we can go on the left, go down to 4. On the top, we're going to go to E, which is the next to last one. So if we go to 4E, it's N. So this is hexadecimal for the letter N. 65 is the next thing on my shirt. So what's 65 equivalent to? I'll let you look at the chart. So I'm going to put it in the chat. What is 65 hexadecimal? What is that letter it represents? E. Zachary's on top of it. Daniel's got it. Yeah, so if we follow the 6 and over to the 5, it's E. Then I've got a 72. 7 with a 2. Mary's got it. And then the last one is a 64. All right, can you put it all together now? Now you can read my shirt. Serendi's got it right there in the chat. So yes, this is probably the most accurate. If you have it in hexadecimal on your shirt, NERD, that's probably the most accurate nerdy shirt there ever is. Because if you write nerd in hexadecimal, it's kind of hard to argue against that. That's pretty much it right there. So that's what my shirt says. Nerd in hexadecimal. I just wore it today because I knew we'd be talking about hexadecimal. I said that's the perfect day to wear that to school. So fun stuff. All right, guys, you've got your assignment. It's just 5 multiple choice this week. Play around with the program there on the next to last page. You know, have fun with the hexadecimal and binary. Next week, we'll be writing a program to play with all that. So that's it. We'll let you guys go. I'm going to visit Mr. Muhammad, sir, and make sure I can get him logged in on Buzz and get his account going. And we will see you guys next time.